you heard these on introduction, and that's a problem. And then I will leave the details of what we actually call routine. So these set of problems that we're interested in state and variable models. I'm sure that almost everyone here, if not everyone, is very familiar with those, but I'm just going to leave this slide over here and set notation to make the rest of the talk easier to follow. So we're interested in this sort of data generating process in which you have parameter theta, you have this hidden or unobserved variable x, and given x, you observe data y. So that's quite common, and I will do some examples later on. So as we observe y, and what we want to do is to perform inference in theta through these, well, we cannot really compute this joint likelihood, the of x and y, because the x are unobserved, so we need to integrate them out, and we have the marginal likelihood here. So the way that we are going to go about doing inference for this is sort of the maximum likelihood fashion. So we're going to be interested in maximizing this quantity, which is the marginal of likelihood. So in a way, it's a more pragmatist approach, but we have to start somewhere. So our goal at the end of the day is we observe y, we want to obtain theta star, which is the maximizer of the log likelihood. As you might notice over here, I assume that we only have one data point y, but normally you would have many of them, and so you have to sum over of those. But for the purpose of theoretical analysis, we just focus on the case one, because then you have a sum, and that's very easy to deal with. So a bit of notation. So these latent variable models do appear quite often. They probably, these historically speaking, they were very well studied in this 1977 paper, which is a sort of summary paper on expectation optimization. And roughly speaking, anything can be cast as performing inference when you have hidden or incomplete data. We will follow into this framework. Hidden Markov models are one example, and if you know that I've been spending a lot of time looking at those. But more recently, they also appear quite a lot in the machine learning literature. In particular, when you want to work on classification tasks, generative modeling, dimension reduction. So there really is a lot of scope for these sort of models. And I mentioned here 3 methods, not because these are the only methods to perform inference in these models, but because they are somewhat related to what we're going to talk about. So the first one is EM, expectation maximization, possibly the oldest one, or definitely one of the most common. I will briefly talk about it to draw connections with what Tim is going to present. Recently, we also saw a lot of variational methods like variational base, variational autoencoders, importance-weighted autoencoders. Those became particularly popular when you have very high dimensional problems because they can scale in a lot better than classic EM, for instance. The last one is simulated annealing, because at the end of the day, what we want to do is to maximize a function. And simulated annealing is a very natural way to do that. I didn't put a reference because I couldn't find one that was like the reference, but there are many. I will show some references which are specific to the problem that we're considering. So I'm going to talk a bit about EM and simulated annealing, just because this will be used to draw connections with what teams were presented. So EM, as the name suggests, is made up of 2 steps, one expectation step and one maximization step. This is an imperative procedure, which normally requires to compute an expectation with respect to the latent variables, to compute this log marginal, the log version to be out of the integral, actually, that's a typo. So we want to compute this marginal log likelihood through computing this integral, and then once we have that fixed theta, we want to maximize this quantity with respect to theta. So E step takes care of the latent variables, M step pushes everything towards the maximizer. Clearly, if you want to do this, and in strict time, you need models which are tractable, only easily tractable, because you want to be able to use that integral and to perform maximization analytically. not very feasible in practice. So for the M step, it's quite natural to use numerical optimization routines instead. Normally, they require being able to compute the gradient of the log likelihood. And I do apologize again, there is also a gradient missing over here. So clearly, this slide is a bit of a mess, but imagine that there is a gradient over here, and then it's all fine. So to compute this gradient, to perform, for instance, stochastic gradient descent or your favorite gradient-based algorithm, and if we want to do it by computing this expectation, then we need to know this quantity over here, which is the posterior of the hidden states during the normally, this is not a very easy distribution, so normally we don't know that. If we are lucky, we might be able to do a simple Monte Carlo, so drawing IID from this distribution. This would lead to what is normally referred to as MCEM, Monte Carlo expectation maximization. Of course, IID samples are not particularly easy to obtain, so there is a lot of literature trying to sample from this posterior using MCMC, for instance, other stochastic approximations, and that led to a whole family of stochastic approximations of PM. I mentioned some references over here. This is clearly a non-exhaustive list, so I just put a few. And more recently, especially because we want to deal with higher dimensional problems, MCMC has been sort of abandoned a little bit in favor of unadjusted schemes because they tend to scale better with dimension. So what I mean by MCMC over there is that normally these are metropolized schemes. So you need to compute the metropolis ratio and perform an separate extent. These does not scale too well with dimensions. So at the expense of using a small bias, unadjusted schemes are preferred sometimes because they tend to be able to tackle higher dimensional problems. So accumulated annealing is a sort of a different twist on the same problem. So we don't distinguish between expectation and maximization anymore. We just go straight to maximization by basically computing the integral and maximizing all in one. So normally, what we will do is to fit an instrumental prior to theta. So we cast the problem of maximizing the marginal likelihood in a Hegel framework now. And we write down this extended, well, this is just the posterior of theta given y, assuming that we have this prior. And as you can see, there is a beta over here. Beta is a parameter, which ideally we would like to take to be very big, because if it's very big, then this distribution will concentrate on the maximal likelihood estimator. So again, we have the same problem, the fact that p theta y is not something that we can compute. So we are going to extend the state space by reintroducing our latent variables. And we consider this extended target, which now is the prior times beta copies of the joint likelihood. So clearly, this requires beta to be an integer. That's the first thing. The second thing is that, again, if you set beta to go to infinity, this will concentrate on the maximum likelihood on theta star, the object that we care about. So it is quite natural to define a tempering sequence, which is a sequence of distributions in which we gradually increase beta. And by increasing beta up to diverging to infinity, if possible, then we will recover theta star. Once you have defined the distribution, you can throw your favorite Monte Carlo algorithm at it. I'm a bit of a biased person in this setup, so I would suggest maybe separating Monte Carlo might be an option. But clearly, once you have this set of distributions, like this sequence of distributions, you can use whatever your favorite algorithm to sample from them. So these are the two bits of literature which we thought were relevant to, and we draw from these ideas to build something slightly different. The last one is a very recent paper by Juan, who happens to be here. So in case you're interested, he's here, talk to him. So he's again inspired by EN, but with a different twist. So we are going from now on, we're going to define this minus log likelihood as u, or sort of easy notation, but also to draw connections with the optimization estimator. And in this very recent paper in A-Stats, they propose an interacting particle system to perform inference and to basically cast EM in a slightly different way. As you can see, this is a set of entities in which now the expectation step appears over here. But there is no clear distinction between maximization and expectation put together. And it does work quite well. So we also build on this particular piece of work. Okay. Last slide of sort of drawing connections is that one other way to look at this problem, we discovered in the simulated annealing literature, is just think about what you would do when you have to maximize a function. So forget about the latent variable model. Let's say you have a function, you want to find the maximizer or minimizer, depending on how you write it down. Then there is a lot of literature on doing this using Langevin-based methods. And that's one other point on which we make connections and we draw ideas to build something that hopefully works quite well. Okay, yeah, I think that I'm done with each of it, so I'll leave it to Tim to go on.
Okay. Thank you very much. Yeah. So, what's going on with the echo set? This is good. Can everyone hear? Good. Okay. Well, thank you for Francesca for introducing this problem and putting it in a kind of wider framework. And thank you, of course, also to Satirius and Denise for organizing this. Almost a year ago, we had the first session, and I met Denise and Francesca, and we started work on this problem. And now we have a finished paper, so it's nice to see the kind of progression through these sessions at Turing. So, as Francesca said, the idea here, if we so the idea the idea from this point onwards, we don't have to put that basic variable models or anything like that. We just want to maximize this particular function, which is an integral. So we want to find the theta for which this integral is largest. So it's like a normal optimization problem, but we're considering an integral across this X space. So we can't kind of naively apply ideas from optimization because we have to calculate this integral. If we don't know what this integral is. And as Francesca said, the idea here is to find a measure which concentrates around this maximizer, and then you kind of force that towards the so it's kind of following from this simulated annealing framework, but in our case we use unadjusted method. So it's more kind of related to unadjusted Langevin algorithms and things of that type. So there's no accept or rejection step. So we use an interacting particle system similar to the one used in our Kuntz paper, which Francesca mentioned, but we add scaled noise to this theta diffusion. And when we add scaled noise, since the noise is non-degenerate, it becomes much easier to calculate the invariant measure. So what we do in our paper is we calculate the invariant measure of this system explicitly. And even though this is an IPS, we consider it more from the perspective of Langevin dynamics. So really our proof is in the framework of Langevin dynamics and uses techniques from that kind of framework. So we don't use much interactive particle system theory. So just to go through the basics of overdamped Langevin diffusion structure is familiar to a lot of people here. So I think Langevin was a physicist, and this was originally a model for particles in a molecular system. But it turns out to be very useful in samples. So if we take an ST of this form, it has a very measure e to the minus. So this fact here is quite exploited. Very convenient when one sample from the density should be expressed like this. You just run the system and it converges to this invariant measure. And moreover, we can rescale the noise here. So if we turn the noise up by making beta large, or making beta small rather, then the invariant measure gets more diffuse. But if we make beta large, then the noise is less and the measure becomes more concentrated around its modal points. And if we set beta to infinity, i.e. we turn off the noise, then it just turns into normal gradient descent. And this measure here, in some sense, kind of converges to a Dirac on the minimizers. because if you have just gradient descent, you're going to get various states when you're in the nest. And this data here is known as inverse temperature. So, yeah, and so this the invariance of these two measures follows very simply from the Fokker-Planck equation. You just get three terms and they cancel out, and it shows have like very much. This realization of this algorithm is known as the unadjusted Langevin algorithm, or ULA. And this is being used for sampling out optimization. So this is in the convex case, the non-convex case, in the superlinear case, and many other cases. There's been a lot of research with these kind of algorithms, and also as part of an EM method. So in this paper here, this is used as a part of an EM method. So calculating the integral, calculating the gradient, we use unadjusted Langevin algorithms. And they have the property that since it's unadjusted, there's no accept or reject. They scale quite nicely at matches. So this is a natural way of sampling from high-dimensional distributions. So let's look at the target measure. So at the core, we said that if we have a W here, then we have the great measure east to minus U. And if we just so if we just do a quick calculation, if we take this function here, and we take the gradient, so we take the gradient with vector theta, and then x1, x2, x3, x4, etc., then we get this this gradient here, which is very similar to the kind of drift coefficient of this system. Consider it as 1 STE. We have this sum here of all the theta gradients, because if we take the theta gradient of the sum, then we get each of these terms. And then when we take each gradient with respect to xi, we just get the xi term in the sum. So if we take the gradient of this function, we get something which is close to the drift coefficient, this xt, apart from the fact we have this 1 over n here, and it's 1 over root n here. However, if we plug this into the Fokker-Planck equation, it turns out this 1 over n and 1 over n kind of cancel each other out in some sense, and we do indeed get the invariant measure here equal to the to e to the minus this sum. So that's the invariant measure of our system with scale noise. As a result, so this is the kind of thing with this simulated annealing idea. When we integrate, so to get the theta marginal here, we integrate over all of these xi components. And since we have since we have the sum here in the exponential, we can split this into e to the minus u, e to x1 times e to the minus u, e to x2, etc., etc. So we can split the integral here into the product of just one integral to the power n. And what is this integral here? Well, this is exactly what we were looking at before. We wanted to maximize. So this is k theta. So our theta marginal here is proportional to k theta to the n. And as n goes to infinity, this will concentrate around the modal points, which of course to maximize the k theta. So yeah, so high n theta concentrates around the maximizing of k as n goes to infinity. And indeed, we can write this in kind of in Gibbs measure form. So if we set kappa equal to minus log k theta, then if we just have one particle, the invariant measure will be minus kappa. If we have n particles, then the invariant measure will be proportional to the minus n kappa. So in some sense, the number of particles n here acts like that inverse temperature parameter. As we add more particles, the measure gets more and more concentrated around the modal points. And there are lots of nice bounds as well from the difference between this maximizer theta star and this theta marginal coming from these work on Manchester Langevin algorithm. So it's inverse temperature parameters what this comes down. In the convex case, we get order x to the minus half, and there are similar bounds in the non-convex case as well. And we get a log factor in the non-convex case. It's more like log n over x to the half, x minus half, or log n over x to the half. So this is kind of framework. So that just makes a quick diagram just to reiterate the point one more time. So if we have these n particles plus the Langevin space, there's one theta particle in the theta space. As we increase the number of particles, theta marginal here, so each shaded region is kind of represented in that. As we increase the number of particles, the theta measure here becomes more concentrated around theta star. So our algorithm here is very similar to the many algorithms. We just take Euler-Maruyama discretization of the stochastic process. So we have step size gamma, and we set our algorithm like this. And we use the convention that the algorithm is involved in pseudocytosis is involved. And given that we're looking at theta marginal of this distribution, we don't really care about this x. I mean, we care about them to calculate theta, or we really care about this theta. So when we look at the error, with no pi, it's going to be scaling the system in this way. So we scale each of these particles to x minus half. And it even turns out using this rescaling, so rescaling using tends to the most hard. It's very nice. And make sure our numeric errors are independent of capital N. So even though the system will be on a very large dimensional space, and we have lots of particles, the numeric error is independent of capital N. And as well, the contraction, when we get to that later, that will be independent of capital N. So this rescaling is very natural. So as I said, similarly, when we're looking at, so here, this is the error between the invariant measure and continuous time process. We rescale the continuous system as well. Indeed, if we do this calculation here, so if we have two complements at the end, the rescale continuous system is set n2, is set tilde n2. And if we calculate the square of the norm of the difference, then we get this expression here, which is entirely in terms of W. So another advantage of using this rescaling is we go from having this number, this gradient with respect to theta, and this gradient with respect to x. When we do this rescaling, it all kind of matches up, and we just get everything in terms of W. So it's as I said, it's quite natural. And conventionally said, this particle pair here, we have one theta and one of the xi, we call that vi. If we end up with getting expressions like that. This rescale system has nice properties and mean of each of these particle pairs. So if we take one, the theta and one of the xi, and sum of each of these pairs by the n, then this is the square of the rescale system. So if we assume convexity here, then we get a nice kind of into the proof of contraction. So we get the sum of each of these terms here. We can apply the convexity assumption, then we get this. And then we apply what I was talking about before, where this Zn here is the sum of the mean of each of these vi. And then this we have the expression this form, from which this is proved to the exponential convergence invariant measure. So it all works out quite nicely and naturally. So as common with this kind of sampling algorithms, our main kind of proof technique, we split the so beta star is our maximizer, beta n is our algorithm. We split it as using the Asher-Slack triangle inequality. We have three terms. We have the difference between the invariant measure, or the beta marginal of the invariant measure, and beta star. We have the difference between the continuous time and the invariant measure, and we have the numeric error between the discretization and the continuous time. And the second is third error, so the difference between the invariant measure and the continuous time process, we bound by comparing what this rescale system Z. And here, this is the rescale invariant measure. So we rescale the system, we rescale the invariant measure as well. And the same with the numerics, we bound comparing to this rescale system. So our assumptions, given this is the first kind of work in this framework, we assume the nicest possible attention. So we assume a Lipschitz assumption, we assume a convexity assumption. And we've written this Lipschitz assumption kind of strangely, because for certain parts of my paper, to do with thinking about it more in terms of the OPS, excuse me, it was convenient to write it like this. But in general, for everything I've discussed so far, we can just replace this with a normal Lipschitz assumption with some L and then a V minus V prime. So this doesn't really mean that much. And then the standard convexity assumption as well, which obviously makes everything very nice. So given this is the first work, we assume these kind of nice conditions, and we get a bound with form. So this costs the difference between beta star and the invariant measure. We have 1 over root n. We get exponential convergence to the invariant measure, and our numeric bound here is independent of n. So this cost the C here doesn't come away. And we get the gamma x to half. So gamma is the step size, and we've used the Euler-Mariano scheme, so we get gamma x to half. And we haven't done the Milstein scheme in this case because it turns out to be more complicated. So it names what Then each of these three bounds, because we're using the theory of large band diffusions, and there's been so much research into unadjusted large band algorithms and these kind of things, this is quite a robust framework, and we hope that we can apply these bounds or apply this framework to a more general position, setting where we don't necessarily see the complexity or Lipschitz assumption. So each of these bounds in different places has been proven under more general conditions. So I hope we can extend this framework in the future. So just to recap, so we want to maximize this function here, which naturally arises in Latent variable models to try and optimize the parameters, as Francesca discussed. And we do this by sampling the distribution that concentrates around the maximizer. And this is very much in the kind of the spirit of its simulated annealing technique, where we use an unadjusted algorithm without an acceptable rejected stage. And we do this using this IPS here, which has a very measured such distribution, where we added a scale of noise to this piece of diffusion. And for theoretical purposes, it turns out to be very useful to use this rescaling here, given that we only really care about this theta, and the x's are just for calculating this theta. So this rescaling turns out to be very natural. And there's one more slide. I don't know if you want to just make some concluding remarks, Francesca.
Yeah. So as you can see from this talk, the idea is drawing from a lot of different literature. We think that this is a good thing in the sense that by combining good ideas from other literature, you might be able to get something which is slightly better or with easier theoretical analysis at least. So this is a bit of a combination of the simulated annealing literature, then you have EM coming in. There is a lot of literature also on interacting particle systems, so one could imagine leverage that side to maybe get something a different direction for theoretical analysis, although we found that the Langevin point of view was the best one to get these non-asymptotic error bounds. This particle method, even if at the moment we don't have numerical experiments, but there are some in Kuntz paper. The scheme is not terribly different. It does seem to scale quite well, so we're very hopeful that also with this addition of noise, it will scale quite well to dimension. As Steve already mentioned, there is scope to extend this beyond the convex case. Dropping the Lipschitz assumption from the point of view of interacting particle systems has also been done, so it's something that already exists, and we could leverage that too. Clearly, Euler-Maruyama is not best time discretization scheme, so there is scope for extending that to other directions. One important point which I think is worth mentioning is that once you have this pi n, which has n copies of your x and one copy of theta, in principle, you can use any sum